Well, hello, welcome again to Math 315, Analysis and Topology, and we're having a look at, this is the fourth video for Chapter 1. This is the fourth and final video for Chapter 1. We've been looking at recursively defined sequences, and I mentioned the last bit we looked at were the Fibonacci numbers, which satisfied this recurrence up the top here. But I tell you the first two numbers, 1 and 1, and to get the next number, you simply add together the previous two numbers. So you get 1 plus 1 is 2, and then 2 plus 1 is 3, and then 3 plus 2 is 5, and so on. Now, in our next example, I give you this recurrence here. So what it says is, it says you take the first number to be 1, you get each new number by multiplying the previous number by this expression, 2n minus 1 on 2n. And we're going to write out the first four terms of this sequence, and then we're going to show that this sequence is in fact what we're going to call a decreasing sequence, and we do that by looking at xn plus 1 minus xn. So here is the solution to this one. So there's our recurrence. We start off with 1, and to get each new term we multiply by this quantity. So x1 is 1. Now x2, you've got to compare carefully here. x2, I'm putting n is 1 up into here. 1 plus 1 gives me the 2. So I'm putting n is 1 into this formula here. So I get 2 times 1 minus 1 over 2 times 1 times x sub 1, which is 1. When you simplify this expression here, but I put some brackets in, I think, you simplify this expression here. I'll put some brackets all the way through so we don't get confused. So we multiply, simply get a half when you plug that in. To get x3, again comparing, this is xn plus 1, so my n is 2. So I put n as 2 in, I get 2 2s are 4 minus 1, 2 times x2 times the previous term in the sequence. Well, that gives me 3/4 times x2 is a half, so I get 3/8. Well, then we do the next one. To get the fourth term in the sequence, we're putting n as 3 in, so I get 3 times 2 minus 1 on 2 times 3 times x3. That gives me 5 on 6, and x3 was 3/8, and that gives me 5 on 16. Now, if you look at these numbers, you see that they are getting... I've got that bit there, right? Yeah, the 3 goes into that twice, so I get 5 on 16. And you can see the numbers, these fractions, are getting smaller. And that's the next part now. We want to prove that the terms of this sequence are getting smaller. That is, it's a decreasing sequence. And the way we'll often do this is to look at the difference between each term minus the term before it. Look at each term minus the term before it. Now we've got a formula for xn plus 1, which I just plug in, and then I've got minus xn. Now we want to simplify this, so I'm going to put it over a common denominator of 2n. So I get 2n minus 1 times xn minus xn times 2n. Now happily, when we take the brackets out, I get 2n xn minus 2n xn cancels, and I just get minus xn on 2n. Now these xn's, we see from what we did up here in our calculations that all of these numbers are positive because I'm just multiplying positive numbers together. So this is positive, 2n is positive, so the whole lot has got a big minus sign here, so this difference is negative, is less than 0. Since all the terms, all the x's, are positive numbers. So, summarising that we've just shown then that xn plus 1 minus xn is negative, and that says xn plus 1 is less than xn. In other words, each term is less than the one before it. Another way of saying that is the terms are getting smaller. Another way of saying it in analysis is to say that this sequence is decreasing. It's getting smaller. It's a decreasing sequence. Now we'll be doing lots of things like this, both here and later. So this is an important example to get in your head. Here's a slightly harder example, but not certainly within the realm of what we're doing. And we're going to define, again, a sequence recursively by this formula. So it says we start with 1, and then to get each new term, we take the previous term, we square it, plus 2, divided by twice that previous term. So we start calculating. So x1 is 1, so I put 1 in. 1 squared is 1 plus 2 is 3 over 2 is 1.5. I'm going to do this using decimals. So on my calculator now I take 1.5, I square it, I add 2, divided by 2 times 1.5, run it through the calculator, and I get 1.417. Now I'm going to take this number and I square it, add 2, divided by twice this number, and I get 1.4142, and then ... We keep going. Now you may, if you look at these numbers here, when you see 1.4142, perhaps you may recognize that this is the beginning of the decimal expansion of the number root 2. So you may have guessed that this sequence is approaching root 2. In fact, we will see this and we will prove this later on more formally. In fact, this is a way of calculating root 2. If you couldn't work out, didn't have a square root button on your calculator, this is one way of calculating root 2 to as many decimal places as you like, in fact. Now, for the moment, all I'm going to do here is I'm going to show that, firstly, that this number, these terms of this sequence are all bigger than root 2. And you can see these numbers are slightly bigger than root 2, and that's going to be true for all n. And I'm going to prove that for n bigger than 1, this is a decreasing, or at least non-increasing sequence. In fact, it's a strictly decreasing sequence. That is, xn plus 1 is less than xn. So the terms are getting smaller. It's a decreasing sequence. So in other words, this is starting out as being bigger than root 2, and the terms are getting smaller and smaller, and they're going to approximate, they're going to get closer and closer to root 2. You can think about this graphically if you just think of drawing a little picture here. And you might think about putting n equals, so putting n equals 1 in, we get 1. So there's the first one here. Then you put n as 2 in, you get 1.5. And so the terms are all bigger than root 2, and I'm going to draw a little line across here indicating the number root 2. And so these crosses are doing, these terms of this sequence are doing something like this. They're starting off bigger than root 2 and they're decreasing. And we will show later in the limit they actually reach root 2. Okay, now the proof of this is slightly more intricate, as you might imagine, and I'll go through all the steps carefully here with you. So here is our sequence, or rather our recursive formula, and we're starting with x1 is 1, and we want to prove that xn is bigger than root 2. Now here we talked a bit earlier about the AM-GM inequality, and now we're going to get to use it to actually do something quite interesting. So I'm going to apply the AM-GM inequality. I'm going to forget about the xn on the bottom for the moment, and I'm just going to say, well, this is just without the xn, the average of xn squared and 2 using the AM-GM inequality is bigger or equal to the square root of the product of these two. That is, it's 2 times xn squared. So just note that I'm using the AM-GM inequality here. And that I can simplify to root 2xn. So if I now look at this quantity, this is just going to be xn squared plus 2 divided by 2xn. So that is going, so you get divided by 2xn. We've already worked out what this is, so I'm just going to divide both sides of this by xn. And I then have xn plus 1 is bigger or equal to root 2n over xn. The xn's cancel and I just get root 2. And that's the first result. We've now proven that xn plus 1 is bigger than root 2, which, by the way, is just the same as saying xn is bigger than root 2, but we'll just leave it as that. So xn plus 1 is bigger than root 2. Now, for the second part, we want to show that this thing is decreasing, and again, we do always do this by looking at the difference. This is one way to prove something is decreasing. Look at each term minus the term before it. So I plug in my recursive formula for this one, which is, there it is, and then minus xn. Again, I put it over a common denominator of 2xn. So I get xn squared plus 2 minus 2xn squared. And I can simplify this a little bit. This is 2 minus xn squared in the algebra. Now, by part A, we saw that xn was bigger or equal to root 2. And that means xn squared is bigger than 2. And that tells me then that 2 minus xn squared is a negative number. If xn squared is bigger than 2, then 2 minus this will be a negative number. That means that this quantity up here, because the denominator is positive, this quantity up here is a negative number. And that tells me finally then that xn plus 1 minus xn is negative, or non-positive, it's less or equal to 0. And that says that xn plus 1 is less or equal to xn. So we can say here that the sequence is, well, I'd probably technically say non-increasing. It is in fact strictly decreasing, but I've only shown at this point that it's non-increasing. Well, we'll see some more of these in the tutorials, and again we'll look at these later when we look at more of these ideas in the next chapter. I want to say just a little bit about so, in fact, just to finish that last example, hence the sequence is decreasing, and it's bounded below is the word we're going to use by root 2. That is, the terms are getting smaller, and it's bounded below by root 2. And that's all we can say at this point. Now, a little bit about the real numbers, and we'll come back in a much later chapter and discuss the real numbers in a bit more detail. But the ancient Greeks once thought that all numbers, they didn't believe in negatives or 0, were either positive integers or they were ratios of integers. That is, they're either fractions or rational numbers or whole numbers. It came to them then as a nasty surprise to discover this number that we call root 2 was neither a whole number nor could it ever be written as a fraction. This caused the ancient Greeks a lot of grief, because for them every number was either a whole number or a fraction. Euclid gives the following proof of that root 2 is irrational in his work, The Elements. And we'll have a look at that one. So Euclid proved that, and it's a lovely proof which all maths people should know. And that is, we're going to prove that root 2 is irrational. You have to bear with me for a second while I find my proof of this one. Here we are. So we're going to prove there's no rational number whose square is 2. That is, root 2 is irrational. You may have seen this proof before, but it's such a beautiful proof I wanted to go through it with you again. So we do it by contradiction. We assume that root 2 is a rational number. That means a rational number means that I can write it as a fraction. So P and Q are positive whole numbers. That's all that says. And I'm going to also insist that P and Q have no common factors. That is, if we've got a fraction like 6 over 8, you can always cancel that down to 3 over 4. So if I give you a fraction, you can always insist that there's no common factor between the numerator and the denominator. If there is one, well, I've cancelled it out, so there isn't. So P and Q have no common factor. That's very important here. Now we square both sides, so we get 2 as P squared on Q squared, multiply the Q squared up, and I arrive at this equation here, which I've called star. Now remember, p and q are integers. These are whole numbers. So I look at this. This says p squared is twice something. So that tells me p squared is an even number. Now when you square an even number, you get an even number. And when you square an odd number, you get an odd number. So if p squared is even, then p must be even. Well, if p is even, then I can write it as twice something. So I'm going to write p is 2 times k, where k is some integer. I plug this back now into equation star. So if p is 2k, p squared is 4k squared, and that's equal to 2q squared. And obviously I'm going to divide both sides by 2, and I can write q squared is 2k squared. Now once again, these are all integers, so that says q squared is an even number. And as we said before, the square of an even is even, square of an odd is odd, so if q squared is even, q is even. But that means then p is even and q is even, so they have a common factor of 2, at least. But we said p and q have no common factors. So perhaps I should say here, so 2 is a common factor of p and q, but they have no common factors. That's what we said right at the beginning, and this gives me a contradiction. And that means that you can't write root 2 as a rational number, and that means root 2 is irrational. And that's a nice little proof of irrationality. Now, we say then that root 2 is an irrational number, and the set of all real numbers consists of all the rational numbers together with all the irrational numbers. Now, this is not the usual way of defining the real numbers. If we define an irrational number as one which is not rational, then we are saying what it is not what it is. And so, for example, saying that a cat is not an elephant doesn't really give me much insight into what a cat really is. In fact, there was much confusion about this set of real numbers until the mid-19th century, when a more watertight definition, and there are now several, was devised by a mathematician called Dedekind. And we will have a look at a little bit more on real numbers in a later chapter, and the construction of the real numbers. Now, also I want to observe that rational numbers are really quite inadequate. So, for example, we can have a polynomial, here's one here, x squared minus 2, which I've mentioned before, have a polynomial which is negative at one point, and then positive at another point, but there's no root in between. In other words, it doesn't cut the axis in between, even though it starts out positive at one point, negative at the next point, doesn't cut the axis. For example, x squared minus 2. If I only use the rational numbers, if I only allow x to be rational, then this polynomial is positive when x is, say, 4, and it's negative when x is, say, 0, but it doesn't cut the axis if I'm only using rational numbers, because it sort of cuts the axis, but at root 2, but that's not rational. Now, there are a number of possible ways of approaching the real number system, and I'm not going to go into too much detail about this at this point. You can define them into existence. This involves writing down all the axioms that that you'd like the real numbers to obey, and then claiming there's essentially one set of numbers that obey these rules. This raises a lot of problems, not only of existence, but consistency and uniqueness, and we'll have a look at the axioms a bit later on. There's a constructive approach. You can use things called continued fractions that I won't go into here, but for example, you can write root 2 as 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 forever, and you can construct real numbers using these things called continued fractions. We're not going to worry too much about this in this course, but a continued fraction of a rational number terminates, whereas an irrational number doesn't. The main difficulty here is that if I give you continued fractions, it's very hard to add or multiply them. One can use decimals, and this is in fact what you do when you're doing this at high school. The line taken in high school is simply to think of the rational numbers, all numbers whose decimal expansion is either terminating, so if you write them as a decimal, they're either terminating or eventually repeating, and the set of all real numbers then consists of the set of all possible decimals. Well, there are some other ones there. We'll be looking a little bit perhaps later at some of these different ways of defining the real numbers. I just want to finish by mentioning just a couple of very important facts about irrational and rational numbers without any proofs. Firstly, between any rational numbers there's a rational number, and that's easy to prove. You just take the average. Between any two rational numbers there is an irrational number. Not just one, but of course infinitely many. Between any two irrational numbers there's an irrational number, and between any two irrational numbers there is a rational number. You can always find a fraction between two irrational numbers. And we may have a look at a little bit of this in the tutorial problems. Okay, well that's the final video for chapter 1.